So then today I will be conducting a brief walkthrough about the week two, what and all theory has been discussed, and some one or two questions also we will solve. So good evening. Today I'm Calvin Joseph, and I'm going to do the week two problem solving and doubt clearing session for the course Digital Control and Switch Mode Power Converters and FPGA prototyping. So this course has been recorded by Dr. Shantanu Kapil, a professor at IIT Kharagpur. And yes, so I'll be doing the week two. So the outline of today's session is like in the previous session of week one, we considered why we are going to digital control, what advantages we will get when you do digital control, the challenges of digital control, then the various control methods, control techniques which are there, current mode control, voltage mode control, etc. Then we also did a brief recap of the various modulation techniques which are there for these switch mode power converters. Also, we had discussed about the implementation platforms which are available, which are used to run the digital control algorithms. So today we will be talking. So in today's thing, this is the brief outline we will do. So first, I'll be discussing about the various sampling techniques which are there. So for digital control, first we need to sample the analog signal, gets converted into a digital signal, and then we will proceed with our the processing of it and the further digital control of it. Next, I will be talking about digital voltage mode control. What are the things which are present in digital voltage mode control? How we are sensing the output voltage, we are generating the errors, what are the requirements are there, what is the resolution of the counter, what are the various ways we can do pulse width modulation in the digital domain. All that will be discussed. Then the digital pulse width modulation techniques also I will discuss. There are three types: counter-based DPWM, or we can have this delay line-based DPWM or the hybrid DPWM technique. So all this I will discuss in detail. Further, I will talk about the various fixed frequency control architectures which are there, the digital control architectures, how for them, where we are taking the sample, what are the requirements of sampling, etc. We will discuss. Also, the variable frequency control architectures, also what sampling requirements are there. In variable frequency, we will discuss about constant on time, constant off time, and hysteresis control. So, and in between these sessions, if you have any doubts and if you have any queries in whatever I'm teaching at any point which I've said, you could please feel free to stop me and to ask me your doubt and query, because this is just basically a problem solving and doubt clearing session. And mostly the goal and the purpose of this session is to give you a recap and so that your concepts will be clear, as well as whatever doubts you have, you cannot directly contact the professor, but through us, you could get your doubts cleared and rectified. Also, this is a very broad and very heavy and complex topic, so you'll have lots of doubts, and it is best to get your foundations clear, because this will set a tone for the further sessions and for the further part of your course. Okay. So now, why are we doing sampling? In digital control, sampling is required. So all the real world signals which are there, that is the current which is there flowing in the inductor, the buck converter's current, or the voltage which is stored, the capacitor voltage, anything, all of these are analog. Now those signals, those analog signals have to be converted into an equivalent digital signal. And then we will run our control algorithms and we will modulate the DT ratio or the gate signal so as to control the buck converter. But remember, the signals in the practical application where it is observed, those are analog signals. And then we take it into digital domain and we do processing. They could also be processed in analog domain, like in the earlier days, they used to use analog control, where the compensator, etc., the feedback, everything was in analog domain. But now we are slowly adding, digitizing some signals, and we are running our algorithms. This we discussed in the previous week about how many levels of digitization, what are the various architectures which can be developed from digitization. So now in this week, the main thing is there will be an ADC. So we suppose we have a signal, that is the output voltage. This is an analog domain. Okay, this is an analog domain. It may have some it will have some value in volts. We will have an analog to digital converter, ADC, that will convert it into some value. Let us say we output underscore digit D, which stands for digital, and it would be a sort of number which represents this voltage. So suppose the voltage here was 1 volt, then this number, let us assume it will be 1000. Okay, this could be 1000 in the decimal domain. Or if it is 2 volt, this would show 2000, etc. So this is how this signal in voltage is converted into a digital value. Now this 1000 could be, it could be in bits. If it was in bits, it could be like 110110. It could be in hex also. Hex, it would be like A, 9, B, C, etc. That depends on the number of bits. So depending on the bits of the ADC, the ADC can be an 8. Suppose the ADC was an 8-bit ADC. That would mean it would have, in case it was 8-bit ADC, the possibility values it could generate is 2 raised to 8 minus 1. So from 0 to 2 raised to 8 minus 1. This would be the resultant digital equivalent of the analog signal. Okay, so we use ADC for sampling. But one more thing to remember is the ADC will have a clock. Okay, there will be a clock signal which goes to the ADC. The clock signal, what it will do, it will trigger the ADC. Once the ADC is triggered, it will take a sample. Okay, it takes a sample. Let us assume it will take a sample. Once, suppose this is the graph of the voltage. Okay, it will take this sample of the voltage. This sample of the voltage it will take, and it will store that value. Next, when we give another sample, it will take a sample here. So the graph of the output of the ADC will look like this. It will look like this. So this analog signal is converted into a digital signal via this ADC. And so the ADC is very important. And another thing to keep in mind is there will be a delay. Okay. Now I give a command signal, the sample signal to the ADC from the clock or for a trigger signal, that now you have to take a sample. It takes a sample. Then instantaneously its digital value will not come. It has to take some time to process to generate the resultant digital signal. So there will be a delay in the ADC, and that is a very important thing which we must always consider in our practical circuits. So we will be showing how this delay, etc., affects our control techniques, etc. Now, this is the output voltage signal. At what instant we must take the sample, all that I will be explaining. Now, this is a buck converter. So as you all know, this is the buck converter which you guys are all familiar with. This is the high side switch or the main switch. This is the low side switch. This is the resistor which we are using to sense the inductor current. This is the output capacitor. This is the load resistor. And this is the feedback resistor divider, which generates a signal which is proportional to the output voltage. So this feedback signal goes over here. This inductor current sense inductor current comes over here. Then some switching frequencies. All this will be used to generate a model. Is used for the modulation technique to generate the respective gate signal Q, and that will go via gate driver, which will generate the signal to drive this MOSFET and this MOSFET, and they will be QH and QL will be complementary to each other, and there will be some suitable dead time has to be inserted so that there will not be a shoot through. Now, in case if this QH is 1 and if QL is 1, then the input voltage will directly pass over here and large amount of current will flow. So to prevent that from happening, they are complementary, and in addition to that, you must insert a suitable amount of dead time. Now, these are the waveforms of a buck converter under pulse width modulation or trailing edge, and we are considering trailing edge modulation. So remember, this is the inductor current. When Q is on, that is the main switch is on, the inductor current rises. When the Q becomes off, the main switch turns off and the complementary switch turns on, then the inductor current starts falling. So similarly, it turns on and it turns off. And this is fixed frequency. That is from here to here. For one cycle, the time duration is fixed. It is T. It does not change. The time duration is fixed. What is controlled is the duration of the on time. That is the duty ratio of this signal. That is controlled by us. That is mid control. Then this is a trigger signal to turn on this, turn on the gate driver, turn on the PWM signal, and the inductor current turns and the inductor current rises. Then it falls. And this is the waveform of the output voltage. So in this graph, these are all analog signals. There is no signal which is digital. All the signals which we have are analog. Okay, and there is a sort of average value of the inductor current is shown by this straight line. Okay, now if you'll observe, the inductor current has a certain ripple. This is the ripple of the inductor current. This is present. Now the ripple will be like around 20 to 30% of the average value of the inductor current. And see, this is the output voltage. The output voltage also will have some ripple. The output voltage ripple will be like 5% of the rated output voltage, etc. So based on your application, based on your design requirements, this inductor, the ripple will change, but there will be some ripple present in the buck converter. And that is because it is a switched system. Now we will consider sampling. Where will we take the sample? So we are considering that we are taking the sample of the output voltage. This is the output voltage waveform, and we are taking the sample of the output voltage. We are taking one sample per switching cycle. If we are taking one sample per switching cycle, so for taking the sampling, we need a sampling clock. We need a signal to say when do we have to take the sample. And that signal is this FSM. This is the sampling signal. So I give the signal over here, and then we take the sample over here. It takes the sample value and it holds that value. Then next I get another sampling signal. It will take the sample over here and it will hold that value. Next again, after a time I get this sampling signal again over here and it will hold this value. So in this manner, I am taking the sample once. Only one sample I'm taking per switching cycle. So you see the output voltage is continuously varying. But when I'm converting it to digital domain, I have only this information. I have only the information at one particular instant. Rest the ripple information, I am losing out of the ripple information because I'm taking only one sample per switching cycle. And this is happening at a uniform rate. Okay, at a uniform rate, I am taking the sample. Is there any doubts in this part?
So, as you stated, there is SOC in a start of conversion signal. So, when does the SOC and the end of conversion signals for an ADC will does the affect here, sir, for the sampling rate?
Could you please repeat one more?
Sir, start of conversion signal is required to start an ADC, right?
Yes.
So, so if FSM we give at that point of time, and when the end of conversion signal was sent by the ADC, then there will be delay in sir. So, how much delay it is permissible, and how it will affect here?
Okay, so over here, we have not included that delay. In this one, I have not shown that delay, and you're correct. So, like when we run in the microcontroller, as you say, we give the signal at this. We give a command at this time. You take the sample of the signal. It will take the sample, and then after some duration, it will finish converting, and then it will give the ADC will generate a signal saying that, okay, yes, I finished converting. And then the digital value is ready for us to read and to run in our algorithm. Okay. But in that time, there is some sort of delay will be there. There's some sort of
Yes, yes.
conversion delay. Yes. So that conversion,
So
okay. Yes.
will be seen here, or will you will be discussing in the futures?
Yeah, I will be discussing in the upcoming slides.
Okay,
Right.
sir. Thank
So,
you, sir. Thank you.
yes, that delay is inherent in this thing, and we will have to take precautions of where we are taking the sample, what sample we take. Any other doubts regarding this? Okay. How's it trailing edge? So this trailing edge modulation is independent of the sampling. Now the sampling is uh, the modulation technique is the trailing edge modulation. Sampling is the sample we are taking, but it is a trailing edge modulation. Why it is trailing edge modulation is because it is in the control. Okay, in the actual control, there will be, let me go to pen. There will be this peak reference value. Okay. This is the peak reference value. Okay, this is your I ref. And this is your inductor current. When inductor current reaches this reference value, then it gives the signal, it resets this Q and this Q falls. Okay, because the Q is falling, that is why it is known as trailing edge. Trailing edge or falling edge, trailing edge modulation. It is linked to that. Yeah. Any further queries? Okay, in leading edge, what will happen is leading edge is like valley current control. So yeah. So this is the graph. I'm just talking about leading edge modulation. Okay. So this is the valley reference, I valley. Okay, this is the valley reference we have, I valley. This is my reference valley current. And this is my gate signal, Q. It is like this, it is like this, and like this. Okay, this is my gate signal. So I will give a trigger when this reaches this minimum value. When the inductor current touches the valley reference, then it generates a signal to turn on the gate. And that is why it is known as leading edge, rising edge. That is why it is known as leading edge modulation. Okay. So someone else was saying something. Rajashekara Reddy, you were saying something?
Sir, in the
Yes, yes.
in the valley current mode control,
Mhm.
so we have, this the point at which the gate has to be on,
Mhm.
we are giving a trigger. But the maximum value, the if the inductor current reaches the peak value,
Uh,
then the circuit automatically takes care of it.
okay, that is a protection feature. See, in this case, we will. So this is for valley current control. Okay, I have a set event. This set event is coming from this one. So I valley, and this is your inductor current. When the okay, and this is my This is the block diagram for valley current mode control. In valley current mode control, this is turned off. Okay, this is the reset pulse. Okay, this is the reset pulse T, which comes out of time period T. So this reset pulse is coming and after time period T. It is fixed, okay? It is known that this reset pulse will come after time period T. So that is not what is actually, creating variations in your pulse width. The variation in this pulse width, is determined by when, okay, so when this inductor current, this inductor current becomes less than a valley current, then it goes high. Okay, this will give 1. This will get set and the time Q will become 1. Okay, so at this instant, when the inductor current is falling and it becomes less than the valley reference current, then this comparator gives high 1 and set. Set comes and Q equal to 1. And okay, this again goes, again the inductor current starts rising. So what happens? Again the inductor current starts rising. Inductor current is more than the valley current and this be 0. But because I've given set pulse, this will hold on to it and Q will remain 1. Q will remain 1. Now, after some particular time duration T, I will give the reset pulse. I give the reset pulse, means when this is high, then this will be 1. And in that case, Q will go from 1, it will become 0. Okay. So now R will come after a fixed duration of T. It will come after fixed duration T. But what is being controlled is when the switch will turn on. When the switch will turn on. And that is why it is known as leading edge modulation. Leading edge modulation. Any further queries?
So that control is
Yes, Ted.
that control current is I value.
Yeah, control current is I value. Yes. So this control current I value comes from the volt, from the feedback loop, from your controller. Okay.
So that decides the turn on of the switch. So
Yeah,
this
that,
value,
yes.
that is trailing edge.
Yes. No, that is why it is leading edge. Leading edge.
Leading edge.
Yes. Yeah. Hmm.
Okay. Okay.
So any other queries? I'll proceed further. Now we will, in the previous case, we have taken only one sample for switching cycle. So this entire duration is a cycle. It is a periodic waveform. And there's a periodic waveform time period T, inductor current is periodic, output voltage also is periodic. Okay. Now we consider uniform sampling, but in this case, we are taking 4 samples per switching cycle. It look like this. So this is your normal inductor current, this there. This is your normal loop, traces the normal output voltage which is there. But we are taking samples over here. Take the sample over here. Then we take the sample over here, sample over here. Taking the sample over here, over here, over here, over here. So one entire time duration from here till here, I have effectively taken 4 samples. I have, if you notice, I have only taken samples of the output voltage. I have not taken samples of the inductor current. See, the inductor current is in analog domain. The output voltage also is analog domain, but I've sampled the output voltage, and the red curve is the digital value, digital version of the output voltage. So I've taken 4 samples of the output voltage in one switching cycle. Okay. One more thing is I don't have Zoom Premium, so this meeting will end in 10 minutes. But I will again start the meeting, so you can again join the link. Okay. So I have taken 4 samples per cycle, and when I take the sample, I will give a clock command here. I will give another command over here. I will give another sampling command here. One more sampling command. One more sampling command. So the time for the sampling command will be T by 4. So the sampling signal. So the signal F sampling, the frequency of the sampling signal will be 4 times the switching frequency of the converter. Okay, so this converter, let us assume it is operating at 1 kilohertz. So at around, so the time period of the converter is 1 millisecond and the switching period is 1 kilohertz. So if I want to take 4 samples per cycle, per switching cycle, I need to have 4 into 1 kilohertz. That is a sampling signal at a frequency 4 kilohertz. Okay. Now, if I want to have, okay, yes. Sai Kumar, you want to say something? Okay. So the normal switching frequency is 1 value, but if I want to take more samples, then I have to increase the sampling frequency or the sampling clock. Okay. Next, we will consider we are taking only 1 sample, but we are having a delay. We are keeping a certain delay. So this is the switching event, whether switch turns on and the inductor current is rising, the output voltage is as it is, and then we are giving a sampling event. This is my sampling event. This is my sampling command. I give the sampling command, it samples the output voltage and it stores that value. Next, I give another sampling command, it samples the output voltage and it stores that value. And so it happens. But this time, instead of taking the sample over here, previous case I took the sample over here, I took the sample over here as such. This time I am taking a sample prior to it, okay, with some delay. I'm taking a sample over here. Instead of taking the sample over here, I'm taking the sample over here. I am still taking only 1 sample per switching cycle, but I am taking it in advance before, okay? And this TS is known as a delay. Now, this TS delay stands for conversion delay. Now, when I take the sample, as someone probably mentioned, I give the start of conversion signal. Then only after the ADC generates an end of conversion signal, then only I can read the ADC's data and I can proceed with my algorithm. So for that, I need to give a certain delay. So this TS stands for that delay. Okay, that delay includes the ADC conversion time. Also, we also include the computational time. All that is clubbed into this value TS, into this time period TS. Any doubts in this?
Sir, from
Yes,
where
yes.
we can get this can we get this value of TS from ADC datasheet?
Yeah, you can get that value from the ADC datasheet as well. Like it will be dependent on the type of the ADC, whether it is there are different types of ADCs and serial ADC, parallel ADC, etc. Based on type of ADCs, there will be a number of clock signals, etc. Some ADCs have a fixed conversion time. Others have a variable conversion time, etc. So that you will need to know. So there will be some sort of clock cycles of the ADCs, and based on the worst case scenario, etc., you can assume this value of TS.
So the sampling frequency and clock frequency are same, right?
No, that is a different thing. See, there will be, let us assume this is my ADC. In this case, FSM. Okay, this is FSM. This is like a certain clock. It is a certain clock to the ADC, but this is the command clock for sampling. That I give a command, now you sample. Next, I give a command after some time, now you sample again. So this is the sampling frequency command signals which is given to the ADC. But the ADC will have an internal clock, or we may have to provide that clock and some other clock, which will be a much faster frequency and which is used for the ADC's operation. Okay, the ADC will have one more clock which will be used for the ADC in its operation and its computation, etc. That is another clock. So this part of the ADC, etc., we will discuss in the future. There's another week where they taught which ADC to select, how to select the ADC, what ADC, etc. So there these things will be covered. So basically now here we just want to focus how we are taking the sample, at what instant we are taking the sample, and we are providing a provision for some sort of delay, which should in actual practical reality, that delay will compensate or will signify the ADC's conversion time and the computation time required by our controllers. Okay. Any other queries?
So actually, then this digital V naught, the one in red, it
Yes,
should
yes.
come only after 3 years, right?
Yes, yes. It should come only after TS. You are correct. Over here, we are just showing it to give you the understanding of the value. But in practical reality, yes, let me just draw. It will be like this. It will be like this. And at this value, it will get updated to this. Okay. It will be like this. Although it has taken the sample over here, it will still remain at this value. And over here, it will update. This will be the way it will happen.
Yes.
Okay. Now, there was a delay, and this delay was kept less than a time period. Okay? It was less than t. TS was less than t. But suppose TS is equal to t, that is, we're taking one cycle delay. So we are taking the sample over here. Okay. And then we're taking the sample over here, and we're taking the sample over here. So this sample which we take over here will be used and processed after this time. Okay, in this time. This is the delay TS. So in the previous case, if you would see over here, I have sampled it NT at KT. Okay, they are both in the same cycle. I will take this sampled value and I will generate my controller output, etc. This is not possible in practical reality, but just for you two guys to learn, for your understanding, we have shown this. So I take the sample over here, and in that particular cycle only I use it. Okay, and with no delay. This is a very ideal case with no delay. Okay, the meeting will end in like 1 minute, and then I will again start the meeting, and you guys can all join. But in this case, okay, I take the sample over here, and after some delay, then I will use it in this KT period. Then I will use that value in this cycle. Okay, so for that, I've taken the sample prior. And so my total delay is TS. But in this case, I'm taking the sample one cycle prior, okay, NT. And then I'm using it after a delay of one time period. That is why it is known as one cycle delay. Are you guys able to see my screen?
Yes, sir.
So I'm taking the sample value over here, but I'm going to use it after this delay of TS. Okay, after this delay, only I will use that sample value. That is why it is known as one cycle delay. Now, in these graphs, we have not shown the output of the controller. Okay, when we show the output of the controller, then you will be able to realize why that delay term is there. So now I'll proceed further. This is for fixed frequency, and you will notice over here it is known as interval two sample. We call it. When the switch is on, main switch is on, the inductor current is rising, and then we turn it off, and the inductor current is falling. So we take the sample of the voltage when the inductor current is falling, then it is known as interval two sample. If we take the sample over here, it is known as interval sampling. If we take the sample over here, it is known as interval two sampling. So for trailing edge modulation, they use interval two sampling, and in leading edge modulation, they use interval one sampling. That is the preferred standard model. There are various research papers regarding that, and if you're interested, you can dig deep into it. Now we will consider constant on-time modulation. So in constant on-time, what is happening is there's a switching event and the switch is on for a fixed duration. The off time is controlled by the loop. Off time is controlled by my control loop, my feedback loop with the controller. But the on time is fixed. The on time is fixed. So effectively, this is a variable frequency control. Okay, where the time period is not same. So this T on is fixed, but this T off will vary. Okay. So again here T on will be fixed. Again this T off will be different. This T off will be different. So so there will not be any sort of fixed time period. So this time period, assume it to be T2, and this time period, assume it to be T1. So it will so happen that T1 is not equal to T2. Alright. But this is a normal operation. It is a normal operation. It is not like a bit of concern that T1 is not equal to T2. So usually in steady state, for constant on time also T1 becomes equal to T2. But it is not always compulsory that T1 should be equal to T2. In most cases, T1 is not equal to T2. Now we want to take the sample. Remember, we are only considering in our whatever we were showing in the previous blocks. So we were only taking the samples of the output voltage. We were not taking samples of inductor current. We were taking the sample of the output voltage. So this is my output voltage is varying. I am taking the sample of the output. But I have a fixed frequency signal of sampling. So this is fixed. This time period is fixed. After every time period t, I am going to take a sample. So I take a sample over here of the output voltage. I take a sample of the output voltage over here. I take another sample of the output voltage over here, another sample over here, and so on and so forth. So what is happening is in this time period, I am taking only one sample. In this time period, I'm taking only one sample. But in this time period, I'm taking two samples. Okay. This time period, I'm taking again one sample. Now, when we do this case, this would result there's no proper synchronization. Synchronization is not happening. We do not have synchronization. And if this is how we proceed, and this is how we do the control of this converter. It will result in what is known as LCO, limit cycle oscillations, where there are certain oscillations in the waveform of the output voltage and inductor current, and that is not desirable. So these limit cycle, okay. Rajesh Sekri, you have a doubt?
So the synchronization you mean between the switching frequency and the sampling frequency?
Yeah. They are not synchronized. They are occurring at different instants. So because they are not synchronized, it results in some nonlinear phenomena known as limit cycle oscillations. So what do we learn? Now, in fixed frequency control, we used a fixed time period and we sampled it at the correct intervals. Okay, they were synchronized. But now in variable frequency control, they are not synchronized. So uniform sampling is not working here. Uniform sampling has some disadvantages. So we will proceed to a manner where we have something known as event-based sampling. Event-based sampling is like if something happens, then you take a sample. If this event happens, then you take a sample. In uniform sampling, it is like take sample now, delay, take sample now, delay, take sample now, delay, take sample. They're at fixed, after fixed intervals of time, after fixed delays, you have programmed it that it will take the sample. And this is easy to implement. Okay, your uniform sampling is easy to implement. I know now I take a sample now. After a fixed time, I take another sample now. After another fixed time, I take a sample, etc. So it is easy to implement, etc. But there are certain disadvantages when we go for variable frequency modulation technique. Here, the modulation technique, which is used to control the DC-DC converters, variable frequency, because it is constant on time. On time is remaining fixed, off time is controlled by your loop. And so the off time changes as per the desired requirement for steady state operation, etc. But we are taking the sample at fixed durations, and that is resulting in a mismatch, and it is not synchronized. So it results in limit cycle oscillation. So we go for event-based sampling. In the event is, this is on, it is on, this is off. Time on time is fixed, off time comes from the loop. On time is fixed, off time will come from the loop. Same. This is the graph of the inductor current. This is the graph of the output voltage. But I'm taking the sample when this falls. When I know that my gate pulse, my PWM signal falls, that time I generate a trigger event and I say you take a sample here. Then when this again, next time when there's a fall, then I take the sample. Next time when there is a fall, then I take the sample. So my sampling is linked to an event. It is linked to an event. It is not just happening by some program needs, by some program fixed duration. It is happening when some event occurs. So when this, it detects a falling edge, okay? It is falling. There is a falling edge. When it will detect that there has been a falling edge, then it will generate this signal to tell the ADC that you must take a sample. And then it will take the sample of the output voltage. So using this method, we are taking one cycle, one sample per cycle. Okay, one sample in one switching cycle. And so now there's synchronization between the switching frequency of the converter as well as the sampling frequency of the converter. They are synchronized. Any doubts in this?
So here, how we will be accounting for that delay in from input to output of ADC transmission delay?
Okay, the delay for transmission. Okay, in these waveforms, we are not actually showing you the delay. But in the practical scenario, the delay will be like this. It takes a sample over here, but it gets converted and it shows over here. Okay. We'll take the sample over here, but only after this time it will give you the updated value. So one more thing to know is you don't know when it will finish converting. It might finish converting over here also. It might finish converting over here also, etc. It might finish converting. Okay, the ADC might take only this much duration to convert. It might take this much duration to convert. But we take the worst case scenario. Okay? and we decide the ADC, etc. for an application. We decide it. And we will tell in our control logic that only after this delay TS, then only you update this value. Then only you update this value. Although in these plots, we are just showing you the sample is being taken, etc. We are not showing that delay. But in your actual implementation, you will not get viewed instantaneously. There's a certain delay. But we will also program that it will read that value, etc. after some fixed duration, after some delay. So that is how we do in the implementation. So all these implementation algorithms, etc., will be discussed in the later lectures.
So the relation between this FSM and sampling frequency and the clock frequency. Because the switching frequency we are taking.
Like which clock frequency are you referring to?
That ADC clock frequency and the sampling frequency.
See, ADC, this FSM is the command signal to trigger the ADC to say you start converting. Okay, it will say you start converting. But internally in the ADC, you have another, okay, there'll be another clock coming to the ADC. There'll be another clock, which is a high frequency clock. Okay. That clock will decide the cycles of internally in the ADC. This ADC cycle is separate from this cycle of the buck converter or whatever converter. This is the internal cycle of your ADC, that ADC chip or the actual ADC device. It will have another clock. Okay, that is the high frequency clock. Based on that clock, that clock will determine the cycle, how much time it takes for one cycle of the ADC operation. So let us say for one particular ADC, it takes like around 12 cycles for it to convert the sample value to a digital value. So that will decide your delay.
Then for every 12 cycles of clock pulse, this FSM will be given.
No. There are two. Okay, let me. Okay. This is my ADC. This is my FSM. This is my high frequency clock. Okay. Suppose FSM is coming at a rate of 1 kilohertz. This might be coming at a rate of around 1 megahertz. Okay. So if I give a trigger to this ADC that now you start converting, and suppose it takes 12 cycles. It is taking 12 cycles. So after 12 cycles, after 12 pulses of this high frequency clock, it will be ready. See, this is my analog signal. This is my digital signal. So after 12 cycles, it will be ready with the sample value of this analog signal. So 12 cycles will correspond to 12 microseconds. Okay. Yeah. So this
can brief on this limit cycle oscillation.
Okay, like
what does it mean?
Limit cycle oscillation.
Because of lack of synchronization, there is a disadvantage of limit cycle oscillation.
Yes.
So, what is actually meant by that in the?
See, there will be some. The inductor current will be like slowly varying. The average value of the inductor will be slowly varying. Over here, you see the average value of the inductor current is fixed. Okay, but when the limit cycle oscillation, there will be a slow variation. See, this is the ripple of the inductor current. There will be a slow variation of this, etc. Like this is some typical example. There could be other cases as well, but we don't want that to happen, right? We want the average current to be fixed, because the average current in the buck converter is actually the load current. Okay, we don't want these variations to happen. Now, all these sort of things, they result in a harmonics, extra, what you say, losses, extra ohmic losses, it results in, because they are generating higher frequency components which are not desired for us. That is why we don't prefer limits. That's why we want to avoid limit cycle oscillations. Any other queries? Okay, so is there any other doubt regarding this event-based sampling? So I'll proceed further. Now we will consider leading edge modulation, where we are doing uniform sampling. So leading edge modulation is like the value current control, etc. I am taking the sample over here. Again, I'm taking a sample over here. We're taking only one sample per switching cycle. So in this, here they are synchronized. This is the ideal case where there's no delay. Okay. Now we will consider intervals one sampling. That is, see, the previous case is an ideal case. It is not practical. It is not feasible that there will not be any delay for the ADC conversion. But in a practical case, there will be some delay. So if I want to have the value ready at this instant, I must take the sample prior to it. So I will take the sample prior to. So in this case, I will take the sample over here. And after this delayed TS, then I'll be ready with the value at this instant. So that is why I will be taking the sample when the inductor, when the switch is on, the main switch is on, the inductor current is rising. I will take the sample at that instant. That is known as interval one sampling. Okay. In trailing edge modulation, we used interval two sampling. That is, we took the sample when the inductor current was falling, when the main switch was off. But now we will be using, in leading edge modulation, we do interval one sampling. We take the sample when the inductor current is on. So why do we do that? In trailing edge modulation, okay, over here. So we are, it's getting compared in this instant. When the main switch is on, based on the reference value, etc., there will be the comparison. And so that reference value might change. It could change, etc. Then the instant at which this will turn off would change, would vary. So where exactly we should take the sample, we do not know. But in this duration, we take at some particular delay by some, take a sample prior to it. Then we can take the sample easily. So that is why for trailing edge modulation, we do interval two sampling, and in leading edge modulation, we do interval one sampling. Okay. So any doubts in this? So we have no doubts. I will proceed further. So these waveforms which we have shown, they are for a typical buck converter. Now we will consider the waveforms for a boost converter. So in a boost converter, this is opposite. The inductor current is over here, and this is the main switch, and this is the auxiliary switch or the complementary switch. All right. So again, we are still considering one sample per cycle. So if you observe, this is the inductor current is rising and it is falling, rising and falling, and switch is on, off. And in the boost converter, when the switch is on, the output capacitor is discharging. Output capacitor discharges. So that's why the output voltage falls. When the switch turns off, then the energy which is stored in the inductor gets transferred to the capacitor, and there's a ESR of the capacitor that results in a discrete jump. Okay, it results in a discrete jump, and then the capacitor starts charging, and this is how in a boost converter there's charging, there's discharging of the capacitor, and there's charging of the capacitor, so that it will, like, maintain the output voltage at around some average value. Similarly, there's a charging of the inductor, there's a discharge of the inductor, but it will maintain some average value of the inductor current. Similar process happens for the output voltage of the capacitor as well. Now I am giving samples for it to take the sample over here, then it will take the sample over here, and it will take the sample over here. But this can be problematic, see, because this is a discrete jump. Okay, we don't know whether we are taking the value over here or we are taking the sample value over here. So to avoid that, we will time shift it. Okay, we will put this delay Ts, and we will take the sample over here, and then we'll take the sample over here. So we will wantonly introduce a time shift. We will take the sample prior to where we want, so that there's some certain duration for which ADC will finish the conversion, and the controller can also compute the command signal which is required. So that is the delay Ts. And so we are also again taking the sample when the inductor current is falling. So it is known as interval 2 sampling. And there is a Ts time delay. Okay. Any other queries? So now let us consider digital voltage mode control. Now we will go to the actual implementation of voltage mode control, how it is implemented digital. So we need an ADC. So the ADC will sample the output voltage. It will generate a V output N. There's a reference value. It will generate the error, which goes to the controller. And the controller will generate a command signal, which is compared with this external RAM. And that will generate the instant where we want to reset our signal. And it is set in a periodic fashion by a particular switching frequency. And this is how we do the digital voltage mode control of the buck converter. So we have an ADC which will sample the value, and then it will have a delay and certain quantization, and quantized values alone it can result in, and it gives a digital value V output N. Now we will consider uniform sampling. So this is the waveform. So now we will be able to understand where exactly is the delay. So I have the switching frequency over here. This is a switching command that I set. I give a set value, so the switch turns on. Okay. When I have given the when I'm giving the sampling command over here. So I'm giving the sampling command, and the switch takes the sample, and the ADC takes the sample over here. Okay. And instantaneously, my compare value also gets updated. This VC of N, which should take some time to, in practical reality, to compute, it is getting instantaneously updated. And that is being used to compare with this SAW2 RAM, and it is used to generate the duty ratio. It is used to generate the duty ratio at that particular instant. Okay, I take another sample over here, and instantaneously, I assume that there's no delay in the ADC, there's no delay in the controller computation, and instantaneously it is generating VC of N. Okay, and that is being compared with the ramp, and I'm getting the duty ratio. Okay, but this is not possible in practical reality, and we will go and view the practical waveform. So the practical waveform is like this. I give a certain delay. Switching period set command will come over here. Okay. I give the command over here, And prior to it, I give a TS delay. Prior to it, I take the sample. So I give the sampling command over here. I take the sample V output and over here. Okay. And after this TS delay, then I generate this VC of N. Okay. After this TS delay, then I'm generating this VC of N. So this is the time delay TS which I was talking about. Although I'm taking the sample over here, I'm updating the controller output over here. So this delay accounts for the ADC conversion time as well as for the controller computation time. And once the controller value gets updated, that updated controller value is used and compared with this staircase ramp generator to generate my duty ratio. Okay. Similarly, then over here, I again give a signal to the ADC2 sample. It takes a sample, and after its conversion, ADC conversion, after controller computation, the controller generates this VC of N plus 1, which is used to compare with the ramp to generate the new duty ratio. Okay, so any doubts in this? This is like the basic concept of actual practical digital pulse width modulation. So
here the average inductor current won't be constant, right?
yeah, the average inductor current won't be constant, just incorrectly shown. But the motive of this plot is to show that delay TS. What is the significance of the delay? Although it is not being shown over here, the V output and sample is being taken. It takes time for the ADC to convert as well as the controller to compute a new updated reference. So that delays TS. Okay, why are we using sawtooth? Is like it is. You could also use a triangular wave, etc., but that results in a different sort of modulation. So for DC-DC converters, it is standard practice to use the sawtooth, and the sawtooth is easy to generate also. So if there are no more doubts in this, I will proceed further. So this is a very important basic foundation for you guys. Now we will consider case with this one cycle delay. I will take the sample over here. I will give the sampling command over here. I take the sample and then I use this sampled output voltage value to, after the ADC gets converted, the controller also uses it, and I'll generate an updated control value over here. So there's an entire one cycle delay is there. There's an entire one cycle delay I have used. So I get time up to one cycle for my ADC to finish its conversion as well as for my controller to compute the new updated value of the controller output, VC of N. Okay, next I take the sample V output N plus 1 over here, but I generate the updated controller output VC N plus 1 after a time delay of one entire time period. So this is how the delay can be varied.
Sir, while we are implementing this in FPGA,
Now,
can we write this delay as a code? Are we will be doing in that way?
there is in the FPGA you're talking about.
Yes. Yes.
Okay. See, ADC can finish conversion. We can take the computed value of the ADC and we can generate the VC of N. But we will update that value in that register only after this delay of TS. Okay, so that all will be written in the code. When exactly we must update on that? What must be the delay? Will be written in the code.
this V naught of n that we are sampling at this point at the
Mhm.
first will be available at the output pin of ADC only after T.
No, that is not what we mean. We are taking the sample we output and over here. It will be available at,
Yeah.
say, around over here at this instant. It will be available.
Okay.
Then it will controller will compute. Okay, controller finishes computation. It will generate a new value VC of n. But still, we will not take that VC of n and put it in that register. Okay, that value VC of n has to be put in a register. That we will only put after the entire time period. Okay, so we are giving, so effectively we are giving the whole control loop, including the ADC conversion time, controller computation time. We are giving it, no, that this much buffer period is there, T, one entire switching cycle period I'm giving you for you to update the value. Okay. So that is the significance of one cycle period. Okay. Any other queries? So I'll proceed further. Yeah. So see the updated value of this vcon of n, it is only getting updated over here. I'm showing you over here. See, the ADC can finish its conversion, it can finish everything, and VC of n can be available over here itself. So over here itself, I can change and go to VC of n can be updated over here itself. I can update it and give VC of n. So here, let us say over here, I finish all the computation. I can update it over here itself. I can update it, but I'm delaying it wantedly. So that delay happens when this becomes 0, then I will update the value. So this is shown over here. This is shown over here. Output voltage sample by the ADC B output n, B ref, B error is generated. That goes to the controller. It generates vcon of n. That would have happened some time back. But only when this event happens, that this ramp signal is 0, then only I will give the command to the register to take the input value of the register, to update the value of the register. Only at this particular event, then only it will read this value of the controller's output. It will read that value and store it into the register. Okay, so the register is a data block, some particular bits, etc. Then we will store this value. It will be held and it will be stored. And only when this command comes, okay, now we have to update the value, then only it will take the input value over here and it will update the register value. So we have this. So any doubts regarding that?
No, sir. This close.
So we have this, okay. This is my ramp. This ramp is coming like this, it is coming like this. This ramp is this sawtooth ramp which we are generating. When it is compared with this VH of n, then only it will generate a duty ratio. Okay? When this tries to become more than this or equal to it, this will turn off, and this is how we generate a duty ratio. And this is NR minus 1. So we have a modular NR counter. Now the number of levels is raised to 2 raised to NR minus 1. Okay. So if I have modulo 4 counter, if I have modulo 4 counter, then this will have a value of 3. And the number of bits I would require it be 2 raised to 2. Okay, that is 4. That also is shown. Now, how will this happen? How will it see this something known as F clock over here? This F clock. This comes like this. F clock comes here, one more clock comes here, one more clock comes here, another clock comes here, another clock comes here, and further all that. So this is this F clock. Okay, this is this F clock. So in total, if there are NR levels, then the clock frequency should be 2 raised to n into FSW. FSW is the effective time period. So this is TS equal to FSW. TS corresponds to FSW. So the clock frequency should be equal to 2 raised to n times the switching frequency. And that can be very high. Suppose my switching frequency was, let us say, 1 megahertz. And this n-bit counter, suppose the n-bit counter was a 10-bit counter. Okay. So 2 raised to 10 corresponds to 1024. So F clock, which I will get, will be approximately 1 gigahertz. Okay, it will be greater than 1 gigahertz. Now, can we use such a very large frequency, etc., to our particular application? It might not be possible. Okay. So if we want to reduce the frequency, what we'll have to do, we'll have to reduce this value of n. But if we reduce this value of n, then this will be more discrete. It would be like something like this. It will be something like this. It will be something like this. What will happen then? The resolution would be poor. Okay, the resolution of possible values of duty ratio would be poor. So we are facing a sort of challenge or a trade-off, or we need to bargain like how much resolution we want, as well as how high the clock frequency we can generate to run this model counter. Okay, so we require a large value of clock frequency if you want to use it very well for high frequency application. Okay, for low frequency application, it might be possible, but that also depends. Let's study this further. So if VH of n was, this is VH of n, and it is generating the duty ratio according to it. If VH of n was lower, okay, by one value, then the duty ratio which would have come would have be of this duty ratio. If VH was over here at this value, then the effective duty ratio which we would have got would have been of this value. So you see the duty ratio, you could see this could either be 0.4, like it could be some discrete value, 0.4, 0.5, 0.6. It may not be 0.45. Okay. So there could be, certain discrete values. There are discrete values of the possible duty ratio. And those discrete values of the duty ratio is known as the resolution. Suppose, let me just explain a little bit more easier ways. You have a scale. Okay? You have a scale. This is my scale. Let us assume it is 0 to 1 centimeter. It will have like some 10 possible divisions are there. So one division corresponds to 0.1 centimeter. So those are the only values. That minimum value which you can measure using that scale is only 0.1 centimeter. Similarly, the minimum possible duty ratio, smallest change in duty ratio which I can get, that is known as my duty cycle resolution. Okay, and it is desirable if I want to have an accurate control, then my duty cycle resolution should be as small as possible. Okay, then only I can, get accurate output voltage regulation, etc. So this change, okay, where's this change? This change is known as QD into TS. Okay, and that QD is actually the clock frequency. You have a clock coming over here, coming over here, coming over here. So that time period of the clock is T clock. So this QD into TS is equal to my T clock. So effectively my QD is equal to, okay, effectively my QD is equal to delta T DPWM upon TS, and my delta T DPWM is equal to T clock. Okay. The change in the PWM, the delta change in PWM is equal to the T clock, and my effective modulator duty cycle resolution is equal to T clock upon TS, which is equal to 1 upon NR. So this is how we generate the duty cycle resolution. It's determined by this counter-based DPWM. So if you want to have a high duty cycle resolution, we need to have a large number of levels. Okay. If you want to large number of levels means corresponds to large number of NR. And NR is generated by 2 raised to n is equal to NR. So n is the number of bits. So if we want a larger NR, we need a larger number of bits. And if we want that, we need to have a very high frequency clock. Okay, high frequency clock to the DPWM, and that might not be practically possible to generate. So that is So there are certain limitations using counter-based DPWM. But one advantage of counter-based DPWM is it is linear. Okay, it is linear. There is no mismatch. Exactly after some time duration, the change, this QD is linear. Okay, doesn't change. Like certain, you see, if we will learn further that the ADC can have certain mismatch. It could be like this. 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 Certain, there are, in process manufacturing and other certain stuff, there are these non-identities occur. All right. So, but in counter-based DPWM, we do not have that issue. It is linear. Okay, so that is one advantage of counter-based DPWM. Next, we will go to a technique known as delay line DPWM. Okay, in delay line DPWM, what is there? We realize that the clock frequencies requirement for the counter-based DPWM is very high. So that is a disadvantage. So now we will have a delay line based DPWM, which consists of a mux. Okay, the mux. Let us assume this is the clock. Okay, one clock comes over here. It gets delayed by some delay lines. Okay, by some particular values of delay lines. And based on the value of this beacon, it will set this VH and it will select, what is a mux? Mux is like this. It is 0, 1, 2, 3 as you. Okay, this is my select line. And there's some signal coming over here. A, B, C, D, etc. And this is the output. So if my select line is 2, I will get output, I will get C. Okay, this is the mux. So this is the 2 raised to n DPWM mux. There are 2 raised to n inputs. This is one input M0, M1, M2, MK. And these are buffers. These are buffers. Okay, this is a buffer. What is a buffer? It is basically 2 NOT gates. Okay, it is basically 2 NOT gates, and they will have a delay. Okay, when a signal will start, inputs. This is my input signal and this is my output signal. Output signal will be, there will be some finite delay. Okay, some value of delay will be there. So what is happening is, if there's a signal comes over here, it's like this. Over here, the signal which will come out will be like this. Over here, the signal will have further delay and come out like this. Where is further delay and will come out like this. So this is how the signal is getting delayed. Okay, this is how the signals are getting delayed. And based on this VHN, I will select which signal I want. So my signal over here, I do not have to generate. I do not have to generate a signal like this, very high frequency signal. I do not have to generate. It is automatically on its own. My signal. I am getting one. So I am just putting one signal like this over here. I'm just putting this clock signal over here, but it is getting delayed like this. I'm getting one signal. I'm getting another signal like this. I'm getting another signal like this. I'm getting, and I have an option to select which signal I want. Which signal I want, I have an option to select. That is how I will give the reset pulse to this one, and it will determine my duty ratio, etc. Okay. So let us see the plot. This is my plot. This is my clock signal I am giving. Okay. And then after some some time here, TC, some delay time, the same signal I'm getting, but it is delayed. Over here at M1, I'm getting it delayed by twice, by further delay. At M2, I'm getting it delayed further delay. Now, I have told VHN over here is equal to 2. If VHN over here is equal to 2, at this instant, for my reset, let us assume, this is my set pulse. My set pulse is coming over here. This actually FSW clock is also my set pulse to my SR flip-flop, SR latch. So this is my set pulse. So I give the set pulse, my switch turns on. And my reset pulse, I have selected it to be equal to M2 of T. And then when this pulse comes, it gets reset and it turns off. So this is how I'm using a delay line based DPWM. Any doubts in this?
VHA of n is set to 2 by
By vcon of n. See, vcon of n, if vcon of n is 2, At the output of the register, I will get VH of n is equal to 2. If V1 of n is 5, it will be 5, and then I will select the M5. M5 I will select. Okay. So in the previous case, what was there is this is my RAM. Okay. And this is my Vcon. So if Vcon of n is equal to 3, 1, 2, 3. Over here it was getting the comparison. But in this case, it is just, and I'm getting this duty ratio like this. I'm getting the duty ratio like this. But in this case, it is getting delayed. Okay. It is getting delayed. It is set over here. It is getting delayed by 1, then 2, then 3, and then it is getting reset, etc. Like that. So I don't need, my clock over here is just one clock. Okay, the frequency of this clock is not high, but the clock is being delayed progressively. It is being delayed, and then I am choosing the desired delayed signal to generate the desired duty ratio. Okay, so this is the advantage. I do not require a high frequency clock, but I'm using a certain number of delays, and I can get a resolution which I want without having to use a high frequency clock. Okay, so yes, you're saying something.
Sorry, you can proceed.
Okay, so yeah, but there is another problem. Now we don't know this delay TC, whether it delay for this one, if delay for this is at, let us say 1 picosecond, the delay for this could be 1.1 picosecond, delay for this could be 0.9 picosecond. We don't know. Okay, see, we design it that it should be 1 picosecond, but because of the manufacturing, the process, and the various tolerances are there, so the delay varies. And because of that variation in the delay of the various buffers, etc., they tend to do this non-linearity. I showed the previous graph, right? Over here. Like, it should be, our graph we want it to be like this, like this, like this, like this. But what graph we could get is probably, let me change the color. But what graph I could get is like this, like this, like this graph I could get. Okay, because of the delay being variable. And that is not desirable. So that is a disadvantage of this method. Okay, how much of delay, how much of nonlinearity is introduced, that depends on the manufacturing and the design, but this has to be taken into consideration. So now we did counter-based DPWM, we found that it is linear, that is advantage, but it requires a high frequency clock. And delay line based DPWM, there is certain nonlinearity which is introduced because of the variations in delay, but we do not require a high frequency clock. So what we do is we combine both these methods, and we come up with a hybrid method. And we take the advantages of both methods and we try to mitigate the disadvantages of both methods and come with a good compromised solution which we can use. So what do we do is we use the modular counter also, and we use the delay line approach also. So the modular counter, it sets the, this is like sets the MSBs. This is for the MSBs. And for the delay line, it's for the LSBs. So the MSBs, let us assume there's a value 1100. Okay, 1100 is a 4-bit number. Okay, I take these two are my MSBs and these two are my LSBs. These two corresponds for the modular counter. These two corresponds for the delay line approach. So what does this approach do? These two will what you say set the course. Course resolution is what, if you guys would have used an instrument like a DC power supply, there are two knobs. Two knobs are there when we set the voltage. We can either vary the output voltage of the DC power supply largely, like it could go from 0 to 3, 4, a large value. Or there's something known as fine resolution, like it can vary in small values like 0.1, 0.05, etc. Those are the fine ways we are fine tuning to get the exact value which you want. And if we want to change it abruptly or rapidly, we have the coarse value. So that is how we are doing. The coarse value, or the approximate range of effective duty ratio is determined by the modulo NR counter, but the actual fine value is determined by the delay line based DPWM. Okay, so we combine both these methods and we try to minimize nonlinearity and we try to reduce the frequency of the clock required. Okay. So this was this paper which came out in 2001, in June 2000. So what is happening? Let us go in depth into this. Okay. This is my counter. Okay, it is counting. It is counting as it is. Okay, it is. It's counting like this. It is counting. When this one touches this value, what happens? This becomes equal to 1. When this MSB bit, see what will vcon of n, so vcon of n has two parts, 1 1 0 0 assumed. Okay. This is the VMS of n and this is the VLS of n. This is VMS of n and this is VLS of n. So let us assume VLS of n is equal to 2 and VMS of n is equal to 5. So when this counter reaches the value 5, okay, when this reaches the value of 5, it will give command 1. Okay, it will go high. Okay, so in this duration, at this instant, it goes high. Then it gets delayed. M0 is the actual one. Then it gets delayed by certain values. M0 delayed, M1 delayed, M2 delayed, etc. Is the screen visible to all of you guys?
Yes, sir. Sorry.
Oh, okay, my time is losing. So now, suppose there's a value 5. Okay, there's a value 5. When this ramp reaches the value of 5, okay, it goes high. It goes high. Okay, this will go high. It will be like a pulse. It will go high. That pulse will be delayed. It will be delayed by some value here, then further delayed by some value, further delayed by some value. And suppose my select line is 2. Okay, then it will select this M2 of t. It will select this value. So when this value comes, then it will give the reset pulse. So it is using both. It is using both the modular counter and it is using this mux-based approach to generate the effective duty ratio, effective duty cycle. Okay, so in this small duration, if you magnify it, then this is happening. And within that, it is computing, getting a final resolution of the duty cycle. All right. So if we use this method, then the required clock frequency is less and the number of bits required also changes. Okay. So if there are no doubts, I'll proceed further. Yeah. So this is okay. Now we'll consider current mode control. We talked about this voltage mode control we studied. Then we consider what is the modulation techniques, DPWM techniques which are possible. Now we'll consider current mode control. So if you remember, in voltage mode control, we are sampling the output voltage. The output voltage is sampled. We are not sampling the inductor current, and we are using only the output voltage information to control our converter, DC-DC converter, etc. It is a single loop control, which I spoke about last week. Now, in current mode control, it is a two loop control. There's an inner current loop and there's an outer voltage loop. Now, we will consider the case. There's a mixed signal based approach. In mixed signal current mode control, what happens? The output voltage is in a digital domain. It gets sampled by the ADC. Okay, but my inductor current is in analog domain. My current is in analog domain, but my voltage is in digital domain, and that is why it is mixed signal based current mode control. Okay, that's why it is a mixed signal based current mode control. Now we'll consider this thing. We have the inductor current is varying like this, the output voltage. This also makes me peak current mode control. So what happens here is basically I am giving this, I'm doing interval 2 sample. When the inductor current is falling, I am taking the sample of the output voltage. I take the sample of the output voltage based on this sampling plot. I take the sample of the output voltage. Okay. Then there's a delay of the ADC, etc. is there. So the delay of the ADC is there. The delay of the controller to compute the new updated value also I will consider. And after this delay of TS, then only my reference value gets updated. So this TS is my delay. Okay, delay which is for the ADC conversion time and a delay for the controller computation time. So this is controller is actually basically a code, a line of some lines of code. Okay, so that also will take some time. So all that is combined into this delay TS. Okay, and through a DAC, I will generate a I reference value. So when the inductor current reaches the I reference value, then it resets it, and so then the switch turns off. So this is known as mixed signal peak current mode control. It relies on interval 2 sampling. The output voltage is sampled and the inductor current is falling. Right? And there's a certain delay which is for the ADC conversion, accounts for the ADC conversion time and for the controller computation time as well. So this is trailing edge modulation with interval 2 sampling. Why it is trailing edge? Because when the controller action is happening, when the signal is turning off, it is falling. That is why it is known as trailing edge modulation technique. Okay. Now we will consider. In the previous case, we were controlling the peak of the inductor current. We are effectively controlling the peak of the inductor current. But what if we don't want to control the peak of the inductor current? We want to control the average of the inductor current. See, many times in buck converter also, if you see, the average of the inductor current is the output load current. Okay, so if we want to control the load current, we have to control the average of the inductor current, right? But in this method, peak current control, we are controlling the peak value of the inductor current. So this would work well if this ripple was less, but when the ripple is more, then we are not effectively controlling the average value. So then in such a case we use average current control. So what do we do is this digital domain, the output voltage is sampled, etc. And we are generating this controller and reference current is generated. But the inductor current, we have another inner loop. The inner loop and the inner controller also. The inductor current is passed through a low pass filter. And the low pass filter, what it does, it will eliminate the harmonics. Okay, the harmonics are the high frequency components of the inductor current to generate the average DC value of the inductor current. And that is compared and generated and passes through a controller and which is compared with the RAM to generate the new reset pulse. Okay. Now, how do we select the low pass filter? Okay, we select it with some particular cutoff frequency. So if you know, you'll remember. So This is how a low pass filter will look like. This is the frequency and this is the magnitude curve. So this is my cutoff frequency. Okay. So this cutoff frequency is usually selected to be FSW by 10. Switching frequency by 10. What will it do is the harmonics or the higher order switching components it eliminates. So you see the inductor current is like this. This is my inductor current. This is my inductor current. It has a lot of harmonics. If we take a Fourier series of it, we take the Fourier series of it, it will have, you say, let us assume this is the, it will have a DC value. It will have a something FSW. It will have something 2 FSW, 3 FSW, etc. We do not want this. So we take a filter like this. We take such a filter. Okay. This will eliminate. So these components we want to reject. We want to reject these harmonic components. We only want to store the DC value. DC value is the average value. So that is why we use this low pass filter. So any doubts in this? So GCC is actually the current controller. See, in earlier cases we have this. Oh, we have this. This is my voltage controller. Now we have an inner current controller as well. Okay, so that will minimize the error between the average value and the reference average value, and that is how we will control it. Okay, that was not there for peak current mode control and valley current mode control. This GCC wasn't there, wasn't required. Now we will go to fully digital current mode control. We did mixed signal where the inductor current was in analog domain, the voltage was in digital domain. Now we will consider where both are in analog, both are in digital domain. So the output voltage is sampled as well as the inductor current also has to be sampled by this ADC. And we will consider a Ripple emulator. Now what happens is, I take the sample of the inductor current over here. I take the sample of the inductor current, and if I want to have the ripple information, if I want to have the ripple information, I have to take samples like this over here at this period, etc. So that I can get the inductor current waveform. So the inductor current waveform I will get is like this. Sorry, it will be like this, like this, like this, like this, etc. So that is how I will have the sort of the ripple information of the inductor current. Okay. See, this is important. I need to have this information. See, if I just take the sample of the inductor current like this over here, just take the sample of the inductor current over here, then further I take a sample and it goes like this, then there's no comparison will not happen. No, it will not. This is my reference value. This is my sampled inductor current. When it passes through a comparator, it will, there is no change. No, the comparator will remain as it is. Either it will be 0 or it will be 1. So either the switch will be fully on throughout the time or it will be fully off. There will not be any change. So to result in that comparator action, which will generate that effective duty ratio, I need to have the ripple information of the inductor current. Now, if I want to have the ripple information of the inductor current, I need to have a very high frequency sampling clock for this ADC. For this ADC, I need to have a very high frequency sampling clock because I want to have the ripple information of the inductor current. But that would result in very high frequency, and that is not desirable because at high frequency losses are more. It might not be practically feasible. It would require it more costly. It might be okay. So we don't want to do that. So what they do is they take a sample. See, they take the sample of the inductor current over here, and there's a ripple emulator internally in the digital block that will emulate the ripple. Okay, it will emulate the ripple with some particular slope MC. It will emulate the ripple with a particular slope MC, and that is how it will emulate the ripple. Now, this does not need to be MC does not need to be equal to the slope of the rising slope of the inductor current. It does not need to be. There are some research papers which say what value of the emulator slope is required. That is a very advanced topic which is not required for you to guys know. But one thing you must understand, this is just the key takeaway which you must have is this emulated current, i.e. emulated current is not the same as the inductor current. This emulated current is not the same as, it need not be same as the inductor current. There are some techniques which they use some samples of the input voltage, output voltage, etc. to try to emulate it, but it needn't be equal to the inductor current waveform. So the inductor current waveform, the actual practical inductor current which is flowing is different from the emulated current in our digital platform. That also is okay. That also is permissible, but we are still able to control our DC-DC converter. And now over here, this comparator is not in digital, it is not in analog domain. It is not an analog comparator, it's a digital comparator. Now the implementing the digital comparator is also for the simpler. Now if you go to previous one, in this case, this is a analog comparator. Okay? It is an analog domain. But this over here, this is in digital domain. So it is easier to implement. It is just a subtraction, etc. And it is easier to implement. Okay. Now, one more thing is one important point which you must understand is there is always a ADC conversion delay. That ADC conversion delay is always there. That is one of the challenges which is there in digital control, which we want to overcome. Now we have understood that we will take a sample of the inductor current and then we will add a slope to emulate, that the inductor current's ripple information. Okay, the ripple information. But I take the sample at the valley. I need to take a sample at the valley. I cannot take a sample over here, take the value, then add the slope. That is not permissible. I need to take the sample over here. At the valley point, I need to take the sample of the inductor current and then I will emulate the slope. I will add a slope. Okay. But you see, I take that sample over here. Immediately, the ADC will not convert and give me the value. There will be a delay. So, but there is a requirement that I have to sample only at the valley point. I cannot sample anywhere else. But there is a delay of the ADC. So what will I do is, I will take the sample of the inductor current over here, but I will wait for a time period T after the time period is elapsed, and I will use that sample value in the next cycle. The inductor sample which is taken in the previous cycle is used in the next cycle for generating the emulated ripple current. Okay. So any doubts in this part till now? If there are any queries, you can stop. Why high frequency ADC? Why do we require high frequency ADC? Okay, let me go to that. So if I want to have the information of the inductor current ripple, okay, if I want to have this information of the inductor current ripple, I need to have a high frequency ADC. If I have low frequency ADC, if I take only one sample per cycle, then the inductor current information is like this, then next it is like this, next it is like this, next it is like this. This is not the information which is having, the ripple information is not there in this. That is why I need to have a high frequency ADC which will provide the ripple information. But the high frequency ADC is not what we want in our actual practical implementation. So we take only one sample of the inductor current and we delay it by one time period, and then we add a ripple to it. And then we add a ripple to it. Okay. We have an emulated RAM. So this will give you a clearer picture. It's my laser pointer. So I take the sample of the output voltage over here. Okay. I take the sample of the output voltage and delete yes. I take the sample of the inductor current. See, the inductor current over here is at this point. Okay? At the valley, this is the inductor current. I take the sample. I hold that sample value, and this sample value of inductor current. In the next cycle, I'm using that to add my ramp emulator. So in this cycle, I will use the previous store value or the valley point of inductor current, and I will add the ramp to that point, to the previous value. I will not add a ramp to the current valley point. I will add a ramp to the previous valley point of the inductor current. Okay. So in the current loop, there is one cycle delay is present. It is always present in this fully digital control architecture. But the output voltage, I can have a smaller sampling delay. With resolution, okay, yes.
Yeah.
Uh,
Sir, actually, like in the actual inductor current,
Mhm.
at the time we are sampling, it appears to have two values.
where over here?
That yeah, the blue color waveform,
Yes, the blue color waveform is
actual
not
inductor
the,
current. This IE.
that is the emulator inductor current. It is not the actual inductor current. The actual inductor current is the orange waveform. So let me just zoom in. The zoom for this. Yeah. The zooming option is okay, just see over here, okay? So the orange one is the actual inductor current, okay? The inductor current which is flowing the circuit. Now I've given the sampling command that you must take the sample. It captures the sample. The ADC captures the sample, and it will convert and it will compute everything, etc. But this captured value of the valley inductor current in this cycle is used in the next cycle, and then to that we add the ramp. Okay. So for this emulated current in this instant, over here we are taking the previous valley point sample and we are adding the ramp to that. Right.
Sir, in the circuit, where we are actually adding in the circuit.
The emulated ramp you're talking about, sir.
Yes, sir. Actually, we are adding the sampling point with the actual waveform at every.
No. See, if you see this one. If you see this implementation, I am taking the sample inductor current. Okay, I'm just taking one sample per cycle, and to it I add a emulated ramp, and that is happening in the digital platform itself, inside the FPGA. It's not physically
Adding is
visible.
happening.
Yes.
Yeah, the adding is happening inside Ripple Emulator.
Yeah, the Ripple emulator is generating the emulated current signal. Okay. So let me just show. I think I to write understand. Okay. Assume this is IE of n. Okay. And this point here is there is a point here and a point here. Okay. This point is I value of n, and this point on the top is I value of n minus 1. So this IE of n uses I value of n minus 1. So IE of n is like this. It uses I value of n minus 1 and it adds the ramp to that. Okay. But the actual valley current at that point is this one. That is, this is I value of N. The actual value point of the inductor current is this, but I use a previous value point and I add the ramp to that. Okay. We choose this. This is something which takes a lot of time to understand. You have to like see the waveform, think it over, understand it, and then you will understand. Of course, it is quite complicated. Takes time. Right, and if bit resolution. Okay, Sai Kumar is asking bit resolution of ADC is less than. Does it affect the emulator? So, no, if the resolution of the ADC is less, yeah, then it depends. Like the bit size of the Ripple Emulator, bit size of the ADC might be a different thing. There could be certain issues. Any other doubts? Any other queries? So I'll proceed further. You can take your time, process it as well. You have doubts also, you can send your doubts or the YouTube, whether YouTube video is uploaded also there also you can comment your doubts also, you can comment and answer it. And you can see these lectures are being uploaded on YouTube. You guys know that, right?
Yes, yes.
So I will actually put this actually. I will send you a link to the YouTube channel as well as with the slides. I will upload the slide also, so you can refer from here. Okay. Now proceed further with the session. So the meeting will end in less than a minute, and then I'll again start a meeting and you guys can again join. This is for fully digital. Now we will go to constant off-time peak current control. So in this case, same, we are using mixed signal. That is the inductor current is in analog domain. The voltage is in digital domain. We take the sample of the output voltage. We use the current controller and generate the reference value, pass through a DAC. Inductor current is compared to it, and then it will generate a trigger. That trigger will set the minimum off time. Okay, and also there's a requirement for minimum. So where I was talking about the mixed signal peak current mode control. Right. So the generated reference current is compared with the actual inductor current, and when it changes the state and when it detects a positive edge, then the constant off time is set. Okay, that constant off time is used to generate the gate signals to the buck converter. Right. So this is my point. Okay. When what happens is if I do uniform sampling, you do uniform sampling with no delay. My inductor current is it takes a sample. I give a sampling signal. It takes the sample of the output voltage, and this is the ideal case, which is fictional case, which is not possible. Immediately, there's no ADC delay. There's no conversion delay. Immediately, the reference gets updated. The reference gets updated, and it would then be reset over here. Okay. Similarly, after uniform sampling, okay, at fixed intervals of time, I'm taking sampling. This is as I told earlier. When we do variable frequency control we have to use event-based sampling. We cannot use uniform sampling because uniform sampling would result in limit cycle oscillations, which are not desirable. So we have to use event-based sampling. But this is showing the case where we are using uniform sampling and there's no delay. So what is happening is the reference current is getting updated abruptly and in between. Now, so this is infeasible. This is not practically possible as well. So in this case, we are taking some delay. Okay. We are taking a sample over here. We are taking the delay. And then we are generating the reference. We are updating the reference. Again, we take the sample over here and we are updating the reference. So what is happening is, in our control loop, we are controlling the output voltage and some particular the sampled output voltage is being controlled. See, we are controlling the sampled output voltage. If we are taking the sample at the midpoint or the average of the output voltage, then the controlled loop will be controlled such that it will maintain that average value. But if we are taking the sampled value of the output voltage at the peak of the output voltage, then we have to set a reference also such that it's the peak of the output voltage correspondingly. So where the point of sampling also is important. Now what happens if you do uniform sampling for variable frequency control is it is changing the point at which we are taking the sample of the output. Once it is over here, another time it is somewhere lower, etc. It keeps on changing. That is what causes those limit cycle oscillations. So to avoid that, we have event-based sampling. What happens is when the switch turns on, then we are giving the sampling command. Okay. Then again, when the switch turns on, then only we are giving the sampling command. So because of this sampling which is happening based on an event, then we are able to have one sample per switching cycle, and it is generating good feasible operation by considering appropriate delay also in the control. Okay, now there are various applications of constant on-time control as well as constant off-time control. Now, constant on-time control is used constant on-time control is like valley current control, and it has advantages. Like let us assume constant on-time. This constant on-time control. This is constant off-time control. Okay, constant off-time control. This is also they use a FOT. Okay, this is known as fixed off-time control. This is constant on-time control. That is there if you see research papers. What they have is they have a monoshot timer. Monoshot timer stores the value of the constant on time or the constant off time as per the architecture, right? And there is something known as an event. Based on that event, I will take the sample. I will take the sample based on this event. When this inductor current becomes more than the peak value, then an event is generated, and that event is used to trigger the ADC to take the sample of the output voltage. It takes the sample of the output voltage and compares with the reference, generates an error, generates a peak value of the reference current, and that is used to control using this constant on-time control. So why should we go for constant on-time control? We have fixed frequency, valley current mode control also we can use. Why are we going for constant on-time control? Constant, see, in valley current mode control, if it was the duty ratio small, okay, the duty ratio is small. This is how small the duty ratio is. Okay? This is if we want the duty ratio to be so small. What would be the requirement in such a case is, this is our requirement based on our particular specifications and our application. And if we want to use valley current mode control in such a case, then the duty ratio will be less than 0.5. If the duty ratio is less than 0.5, valley current mode control is unstable. So it is not possible for us to use. Similarly, at these transitions, when the switches turns on and off, there are certain spikes. Okay, those spikes are undesirable. Because of the spikes, what do we have? We have a blanking period. And because of this blanking period is then fixed frequency. Because of this blanking period, what will happen is there will be a limit on the minimum duty ratio. The minimum duty ratio which is possible will be limited because of this blanking period which is there. Now that, so we have to choose one alternative. Okay, we choose one alternative. So constant on-time control is very good alternative. If we want to maintain this small time, that we can easily program into this monoshot time. We can program it that it should be on for the small duration and then turn off. So that is why we can use, that is why constant on-time control is very popular. It is used in various multi-phase applications, etc., where the step down ratio is very small. It is very useful. And another advantage of constant on-time control is it is, if we just sense then this inductor current, this is the inductor current. We just sense this inductor. Let me just change this. Okay. If I just sense this is the current which I am sensing. Okay, this is the current which I am sensing. I am only sensing the current of this low side switch. If I'm sensing the current of this switch, it will look like this. When this is on, this current will be 0. When this switch is on, then the current will be equal to the falling current of the inductor. So if I'm only sensing this current, and it is easier to sense this current, it is easy, cheap as well, then I can do valley current mode control. Then I have to use valley current mode control. But if I use valley current mode control for low duty ratio operation, it is unstable. So I will use constant on-time control. Constant on-time control does not suffer from this stability issue. Right. So that is an advantage of using constant on-time control. Then we also can use fixed off-time control or constant off-time control, that is equivalent to peak current control. Right. So based on a particular operation, we can either go for constant on-time control or fixed off-time control. And peak current control is unstable for duty ratio greater than 0.5, but fixed off-time control does not have that issue, does not have face that problem. Okay, no problem for duty ratio greater than 0.5. Right. Now we will go to hysteresis control. So these are variable frequency control techniques. Does anyone have any doubt? I'm sorry, I forgot to ask about that. Okay. So proceed with hysteresis control. So this is also, a variable frequency control technique. So both constant on time, fixed off time, all of those are variable frequency current mode control technique. Even hysteresis current mode control technique also is one of this. Okay. So what happens is we have a hysteretic comparator, okay, and that is made up of this sort of block. We have an inductor current. There is a peak value. This is known as the peak value, and this is the valley value, I value, and delta I is the ripple. Okay, this is my ripple. So I reference is the peak value. This orange thing is the I value, and IL is the inductor current, which is varying like this, and delta IH is my ripple. So when the inductor current tries to become more than the reference current, UR becomes 1 and it resets it. It resets it, then the switch turns off. When the inductor current tries to become smaller than the valley current, then this set pulse comes and it turns on the switch and it is turned on. So this is how hysteresis current mode control. We are able to control the current and keep it in a band, okay, as per our requirement. Right. Any doubts in this hysteresis current mode control? This is like a very, very layman method of, this is simple method which if you ask someone to understand how you want to control something, they say when it tries to go above some particular value, you turn it on. When it tries to go below some certain value, you turn it on. This hysteresis control is used in our previous refrigerators. Oh, sorry, not refrigerators, air conditioners. Okay. So I'll proceed further. For analog current mode control, hysteresis current mode control. This is the architecture. Now we want to digitize it. So this part remains in analog domain. All this area, this part is in digital domain, and this part is in analog domain. Right, where the comparison happens, and that's why we need to use DACs. Right. But if we use this, the number of DACs and analog comparators increases. There is a provision where we can use a single ADC and single DAC, and we can proceed with it. So, any queries and doubts, please ask me. Please tell me. Because the objective of the session is to clear your doubts. So, if there are no doubts, I will proceed to the questions. Okay, Rajesh, you want to ask something?
So here, the SR latch is in analog domain.
Yeah. It is analog domain.
Latch is there in analog domain.
No, we when
Sir?
this is correct. No. This will be in digital domain. So actually, this US and UR, these signals will go to your what do you say? To your digital platform, FPGA, and this SR latch will be implemented inside the GR. Sorry, this will be in the digital domain. That's a good observation. Thank you. Any other doubts?
Sir, we will go through this recording again, and if you have any question, can we ask in the YouTube channel?
Yeah. Just put it in the comments. Okay. Yeah. Also, like it's advisable to go through the previous NPTEL course, control and tuning methods, to understand about these current mode control techniques, right? Like constant on time, why we need minimum of time. All those is given, those have been taught in those sessions. So you can go through it and learn it. Right? Hysteresis control, etc. All of that is taught. So though that will, some queries and doubts will be further reduced also. Right? You get better understanding about it. Any other queries? So this is one simple question which I made. You guys can let me know. For the counter-based DPWM, that is the first technique we study of DPWM. What is not true? Is the counter's output, does it vary linearly? In DPWM, there are 2 raised to n minus 1 levels. Or the clock requirement is high for counter-based DPWM. Which of them is not true? Hmm. Yeah.
It's motherboards.
Yeah, one of them. So all of these are true. These are all are true for counter-based DPWM technique. And see, there is a 4-bit modular counter, hybrid DPWM technique, and 2 bits are using delay line. Then what will be the duty cycle resolution? Hmm?
or
will be
will be
actually the total number of bits will be 2 plus 4, so it will be 6. Okay,
yes.
and delay line introduces 2 bits. So the effective duty cycle resolution is 1 upon 2 raised to n minus n r. That comes out to be 1 upon 2 raised to 6 minus 2. That is 1 upon 2 raised to 4. Okay, this is the duty cycle resolution. Now, will there be non-linearity issue in this case?
no?
Yeah, there will not be a non-linearity issue. No, there will be. There will be non-linearity issue. Although the amount of non-linearity issue will be less because we're only using 2 bits for the delay line, and those 2 bits in the delay line, which are the least significant bits, they cause the non-linearity. Their non-linearity can creep into the system. Okay. Yeah. So that's all.
Non-linearity we mean,
Yes. Yes. Still.
sir.
Yeah. Yeah.
Uh, non-linearity we mean the size of the step varies,
Yeah. Size of the step would vary. Like if you
or the duration of the particular step will reduce, something like
both happens. Both happens. Then only it becomes
that.
non-linear. There could also be some missing codes or like this is if you go through the data sheet of an EDC also you will see all these things are there.